Hello. Today's lesson is on diffraction gratings. We're going to start by talking about what diffraction gratings actually are, and then we're going to do some calculations with diffraction gratings. And finally, we'll talk about some of their applications as well. Let's start by recapping Young's double slit experiment. In that experiment, light is passed through two slits. It diffracts from these slits and is projected onto a screen where we see a pattern of light and dark fringes form. These form due to interference of the light from the two different sources. The reason Young's double slit experiment is important for today is it's very similar to the diffraction grating. In the diffraction grating, instead of two slits, we have a series of many slits, generally hundreds or even thousands of slits per millimeter. When we observe the light that passes through the diffraction grating, we observe a diffraction pattern. This diffraction pattern consists of many bright points of light. We call these bright points of light the orders of the diffraction pattern. For example, in the center we have the 0th order of the diffraction pattern. Going up we have the first order, second order, third order, and so on. The reason for these bright spots is the light coming from the slits is meeting in phase at these points, and therefore we get constructive interference. In the first order, for example, each slit and its neighbour has a path length difference equivalent to lambda, meaning that the light will meet in phase. One important difference between a diffraction grating and a double slit is that a diffraction grating will split the light up into its component spectrum. For example, white light, as we know, is made up of all of the colours of the spectrum. Therefore, passing white light through the diffraction grating allows us to see all of these different colours. However, there is an exception that in the 0th order, the light will remain the same as it is when it's passed through the diffraction grating. Here's a question for you to have a go at yourselves. Pause the video and have a little think about this question. I'll give you the answer shortly. And the correct answer is violet. What you may have noticed before is that light with a shorter wavelength, for example violet, is diffracted through a smaller angle than light with longer wavelength, for example red. And here's a second question which is a little bit more extended. Pause the video and I'll give you the answer shortly. And here are the answers. Firstly, the light from adjacent slits has a path length difference of one wavelength, meaning that the waves will all meet in phase. Therefore, we'll get constructive interference in this first order. We have an equation that lets us calculate the angle of diffraction. It's that d sine theta is equal to n lambda, where d is the distance between the slits, n is the order, 0th, first order, second order, etc., and theta is the angle of diffraction. Here's a chance for you to have a go using the equation yourself. Firstly, have a look at the image on the left, which shows a real diffraction pattern formed from an LED. On the right are some questions. Pause the video and I'll give you the answers to the questions shortly. The first question asks, how can we tell that the LED is producing two distinct colours of light? Well, the answer to that is very simple. In the 0th order, we can see that the LED is just yellow. However, in the first order, when we split that yellow up into its component spectrum, we can see two colours, a red and a green dot. Next up, we're looking to calculate the spacing between the lines on the diffraction grating. The first thing to realise is that 300 lines per millimetre is equivalent to 300,000 lines per metre. To calculate the value d, all we need to do is do 1 over this 300,000, and we get that d is equal to 3.3 times 10 to the minus 6 metres. Finally, we're looking to calculate the wavelength of the light. We should note that we're looking for the light in the first order, that is when n is equal to 1. We've also just calculated d in the last part of the question, which is 3.3 times 10 to the minus 6. Putting our values into the equation, we get that lambda is 550 nanometers. Finally today, we're going to talk about some of the applications of the diffraction grating, which is a very important optical device. One of its main applications is to use the fact that it will break light up into its component spectrum. This can be important, for example, when observing the light from stars. By looking at the absorption spectrum of these stars, we can perform spectral analysis to work out which elements must be constituents of them. A very similar concept to the diffraction grating is used in X-ray crystallography, which allows us to measure the structure of solids at the atomic scale. When X-rays are passed through solids, they diffract in the gaps between the atoms. This allows us to get some idea of the spacing between those atoms. One of the most famous applications of X-ray crystallography was when it was used by Rosalind Franklin, as well as Crick and Watson, to allow a determination of the structure of DNA.